All right, so this section is still incorporating the calculations from like the 12.2 and 12.1, but we're going to look at it in terms of limiting reactants and the percent yield. So a limiting reactant is the reactant that determines the amount of product that can be formed in a chemical reaction. So pretty much reactants do not get used up at the same rate in a reaction. And the limiting reactant is the one that is used up first, because once it's gone, the reaction has to stop because there's not the proper ingredients left to finish the reaction. So then the excess reactant is any reactant that cannot be completely consumed by the full reaction due to the limiting reactant. So how do we figure this all out? First, you're given a problem and you always need to make your equation. So silver metal reacts with sulfur to form silver sulfide. What is the limiting reactant when 50 grams of silver is reacted with 10 grams of sulfur? Do not just assume that because there's fewer grams of sulfur that it is the limiting reactant. You're actually going to have to do math. So starting with your reaction, we have silver plus sulfur to produce silver sulfide, which would be Ag2S, since sulfur is a -2 and silver is a +1. So that means we have to balance the equation and put the 2 out in front of the silver. So you start with what you're given. The first one is 50 grams of silver. And we need to convert these into moles. So you do that with 1 mole of silver to the mass of 1 mole of silver from the periodic table, 107.9 grams. And that will get you 0.46 moles of silver. Then you proceed to do that again with the mass of sulfur. So 10 grams of sulfur, and we need to convert that to moles of sulfur. So you use the mass from the periodic table, which is 32.07 grams of sulfur, and you should get 0.31 grams, or moles, moles of sulfur. And then, so that step, not too strenuous. This is the new step. You take the amount of the larger number here, so 0.46 moles of silver, and you use your mole ratio. So we have 2 moles of silver to 1 mole of sulfur. And you do that, and that determines that you need 0.23 moles of sulfur required in order for this reaction to use up all of the silver. So then you look back at your moles of sulfur, and you see that 0.31 is greater than 0.23. That means that there are 0.31 moles of sulfur present in the reaction in 10 grams, because it's telling you you have 10 grams. You have 0.31 moles present, and 0.23 moles of sulfur are required. So we have excess sulfur, correct? So your excess is going to be sulfur, and then your limiting will be silver. So what you need to be comparing in these problems is the amount of each of these that are present compared to the amount that is required. So if the amount present is greater than the amount required, that will be your excess reagent. Oops, sorry. You're still writing. Right here, your final answer is, it's asking for what is the limiting reagent, so technically just the limiting reagent one.
Could you have done it the other way, like 0.31 mole sulfur and then done 1 mole sulfur?
I believe so, yeah. All right, so continuing, we still are using the same information from that first problem, so the 2 silver plus sulfur yields Ag2S. What mass of excess reactant remains when 50 grams of silver reacts with 10 grams of sulfur? Sulfur and silver were not like the two best elements. I feel like I keep mispronouncing what I want to actually say.
Is there a 2?
Yes, Ag2S. Anyways, so we had said that from the previous equation that there was 0.31 moles of sulfur present, and we have 0.23 were required. 0.23 moles of sulfur were required. And so the questioning is asking us how much of the excess reactant, which was sulfur, so that's why we're only looking at sulfur here, is because that was the excess reactant. So how much is left after the reaction? So the first step here is to figure out how many moles are remaining after the reaction. So to do that, you simply subtract the moles present minus the moles required, and you should get 0.08 moles are remaining. And so it's asking for the mass, so then we just need to convert this 0.08 moles of sulfur remaining to grams of sulfur. So 0.08 moles of sulfur. So 1 mole of sulfur to 32.07 grams of sulfur. Again, the 32.07 comes from the periodic table. And we have a remaining amount of 2.57 grams of sulfur. You could have with these deals with the mass of the product. And so with the mass, if it's asking for the mass of the product, you must remember that the limiting reactant determines the amount of product. So that means all your math must be dealing with the numbers based on the limiting reactant. So in this particular example, again, we're using the 2 silver plus sulfur and the silver sulfide. Your limiting reactant was silver, and that one produced 0.46 moles of silver, or used up 0.46. So then we just need to convert this moles of silver into grams of silver sulfide. So again, just stoichiometry problems from yesterday. So your starting point is 0.46 moles of silver. And we have 2 moles of silver to 1 mole of silver sulfide. And 1 mole of silver sulfide to the mass of silver sulfide, which would be 247.87 grams of silver sulfide. To get your mass of silver sulfide, you take 2 times the mass of silver from the periodic table, which is 107.9, and add that to the mass of 1 times sulfur, which is 32.07. Add those together and you'll get 247.87. Do you remember doing that in a couple assignments ago?
Yeah.
Okay, yep. So then when you do that, you get 57.01 grams Ag2S.
It'd be hard to make the ideal conditions.
The ideal conditions are hard to be met. There's a lot of experimenter error, misreading a measurement. A lot of times if a gas is produced, it's near impossible to capture all of the gas in order to take a measurement. So there's just a lot of things to factor in when you are doing these experiments. So potassium chlorate decomposes when heated in the presence of a catalyst. In a certain experiment, 40 grams of potassium chlorate is heated until it completely decomposes. What is the theoretical yield of oxygen gas? The experiment is performed and the mass of the collected gas is found to be 14.9 grams. What is the percent yield? So, like always, your first step has to be to write the balanced equation. So, potassium chlorate is KClO3. It's decomposing into potassium chloride, just KCl, and oxygen gas. So we have to balance it out because our oxygens are not balanced. So we'll put a 3 here and a 2 here and a 2 here to balance it. Then you start with your determining your theoretical yield. And so we do the math, 40 grams of potassium chlorate. And we want to figure out the theoretical yield of the oxygen gas. So we need to go from grams of potassium chlorate to grams of oxygen. So we need to first convert the grams of potassium chlorate into moles of potassium chlorate. You do that with the molecular mass from the periodic table. Your molecular mass is 122.55 grams of potassium chlorate. And you get that from doing the 1 atom of potassium plus the 1 atom of chlorine plus the mass of 3 atoms of oxygen. And then we can use our mole ratio to convert from the moles of potassium chlorate into the moles, 3 moles of oxygen gas. Ooh. And then you can take your 1 mole of oxygen gas into grams of oxygen gas, 32.00. Any questions where any of those numbers came from? Why do we have 32 for the mass of oxygen gas and not 16? Because it's O2, good. So when you run the math here, you should get 15.67 grams of O2 as your theoretical yield. And then the last part is asking for the percent yield if in an experiment you actually got 14.9 grams of oxygen gas. So we look at the actual over the theoretical times 100. So in this case, our actual yield was 14.9. The theoretical should be what we got when we did the stoichiometry over 15.67. And you multiply it by 100, and you should get 95.09% was your percent yield. So you were short by about 5%.